In this video, we're going to learn how to compute some of these double integrals, at least over rectangles. So let's say we have a double integral, so two integral signs. We have a function of two variables. We do dA. We're integrating over some rectangle, and that rectangle I'm going to say is AB crossed with CD. So the x values range from A to B, and our y values range from C to D. Let's imagine what we're doing with this thing, or let's imagine that we want to do what we did with partial derivatives and keep one of the variables constant. Let's say let x stay constant. Then we could say integrate our function over y, and just imagine x is just a number that's in there. We don't really care what it is right now, but we're integrating over y, and the y values range from c to d. This is an integral. We could call it a partial integral if we want to, but we don't really do that. But we'll just say that we're integrating it with respect to y. Now, normally, if we integrate a function of one variable like this, since this is really just a regular Calc 1 integral, just we have an extra variable sitting in here. But normally when we do that, we end up with just a number. But because the x can vary in here, and we'd get different values of this integral for different x's, technically what we have here is a function of x. We could even say it's the function a of x equaling this thing. Now, if our double integral does represent a volume of a solid, so we'll go ahead and look at the function that we looked at in the last video, this function x squared plus y squared over 20, where we have the rectangle down here be from 1 to 2 crossed with 2 to 3. So the x values are going from 1 to 2, our y values are going from 2 to 3. If like I said, we're fixing x to be a particular number. So maybe I'll say let x be this slider a. That will give us a plane in three-dimensional space, and that will cross through the thing that we're trying to take the volume of. And you can kind of imagine what we're really doing here is we're finding the area of the cross section of that's inside there. And as we move the slider, we're going to get different cross-sectional areas for each value of x that we were to plug into this function a. And that's why we're using the letter a for that. It's the area of the cross-section for that particular value of x. If we want to find the volume of the solid, what we can essentially do is add up these areas. Of course, doing that through an integral. So we would go ahead and take what we have here, and we'll integrate it. And we'll say that's going to be our volume. Our volume is going to be integral of this a of x dx as x varies through all the values that we can take, so from a to b. Of course, a of x is this integral. So really what we're doing is we're taking the integral of an integral. This first integral integrates over y and ends up only leaving x's in there. The second integral is an integral over just x, and we end up with a number overall. This is what's frequently called an iterated integral. Meaning that we're doing it multiple times, multiple iterations. Frequently what we'll do is we'll leave out the brackets. So we'll write this as something like integral from a to b, integral from c to d of f of xy, dy dx. So notice here that the the order of the integral signs is opposite the order of the variables at the end. So the integral from c to d corresponds to the dy. The dy tells us which variable we're integrating over, and then the integral from a to b, that time we're integrating over x's. So we need to make sure that we know which of the integral signs does correspond to which of the variables at the back. So that's why I kind of think of these normally as like brackets in a sense. So the this integral sign is paired with that dy as brackets around the function. Same thing with this integral sign, the dx. It's brackets over the whole thing. But what that's essentially doing, since we're treating the volume as a double integral, so this double integral over f of xy dA, we can essentially compute that double integral by integrating twice. Let's look at an example of computing an iterated integral. So here we have an integral over the function 6x squared y minus 2x. Now they've written it as an integrated integral already. We could actually write this as the double integral over a rectangle of this function. And when we write it as a double integral, we write it with dA, where the rectangle is just going to be, so the x values are going from 1 to 4, our y values are going from 0 to 2. So this is the rectangle given by crossing 1, 4 with 0, 2. That's the way you can think of it. Whether or not that actually represents a volume just depends on whether or not this function ever becomes negative on this rectangle. I don't know. I haven't looked at it. But that's not really what we need to be doing to actually do this problem. Doing this problem just comes down to doing integration, just integrating directly, working from the inside outwards. So I'm going to leave the integral dx with the integral from 1 to 4. I'm just going to leave that alone for now, and I'm going to work with the inside. The inside, the integral from 0 to 2 of this function dy, I'm going to look at what is the antiderivative of this. Think in terms of partial derivatives. So if I were to treat this as the partial derivative with respect to y of some function, what would that function necessarily be? Minus whatever constants we might need to throw in there if we were doing this in more generality. But we're going to end up with some antiderivative that we'll evaluate from 0 to 2, but we'll still have the integral dx on the outside. Now, what would we have to do for the 6x squared y? Well, keep in mind x squared is being treated as a constant, so really we're integrating over y. What is the integral of y? Well, that would be a 1/2 y squared. But then we have the 6x squared that's still in there. So we'll solve the x squared. The 6 will go ahead and combine with the 1/2. And we'll get a 3. If we look at 3x squared y squared and we differentiate that with respect to y, we will get 6x squared y. That's what we're looking for. Now with the minus 2x, that doesn't have any y's in that, but that does not mean that we can kind of ignore it. Because keep in mind, when we're integrating a constant, we end up getting a copy of the variable. So the derivative of 6x with respect to x is 6, and so the integral of 6 is going to be 6x. In this particular case, minus 2x is a constant, so we'll end up with that constant times the variable here being y. So we'll end up with a minus 2xy. And again, you can always check yourself by going the other way. What is the derivative of minus 2xy, or the partial derivative with respect to y specifically? It would be minus 2x. And that's what we're looking for. Before I mess with the integral with respect to x, we'll go ahead and evaluate over these particular values. So we'll go ahead and plug in 2. If we plug in 2, we get 3x squared, 2 squared. 2 squared is 4. 4 times 3 is going to be a 12. So we'll get a 12x squared. We plug the 2 in here. 2x times 2 is going to be a minus 4x. And then, of course, we subtract what we get when we plug in 0, but 0 is just going to make both of these zeros anyways. So we'll have 12x squared minus 4x. And we'll integrate that with respect to x and evaluate that from 1 to 4. Now, at this point, it's just a regular Calc 1 integral. We don't have to worry about partial integrals or partial derivatives or anything like that. What is the integral of 12x squared minus 4x? Well, did I say? I might have said derivative, but I mean the integral of this. Well, integral of x squared is 1/3 x cubed. 1/3 of 12 is going to be 4, so we'll get 4x cubed. Integral of x is, again, 1/2 x squared, but 1/2 of 4 is 2, so you get minus 2x squared. We're evaluating from 1 to 4. Go ahead and plug 4 in there, so we get 4 times 4 cubed minus 2 times 4 squared. And then we subtract what we get when we plug in 1. So we have 4 minus 2. If we work all this out, the 4 times 4 cubed actually makes it rather big initially, but then we end up subtracting stuff out. We should get 222 as our result. So not really too complicated. It's just doing it multiple times. That's mostly because we're working with rectangles right now. When we get things a little bit more complicated, when we get more general regions, things will get a little bit more fun. But for now, that's what we have. Now, of course, when we found our formula for the double integral, what we did was we held x constant. There was no reason why we couldn't do the same thing for y and get another formula where the inside integral is with respect to x and the outside integral is with respect to y. But we should get the same value either way. And that's what's stated in this theorem. This is a theorem named after Fubini, and it's saying that if we have a continuous function on a rectangle, then we can find the double integral of that function over that rectangle by integrating in either order. It doesn't matter. We get the same result either way. And that still remains true even if f is not completely continuous. If it's discontinuous only at some points or some curves, then it could actually still work as long as we do have, as long as these integrals do actually exist still. Now, naturally, we are skipping over quite a bit of theory here. When we designed all this, we did make the assumption that the integral of our cross-sectional areas should be the volume of the solid, and therefore it should be the value of the double integral. That was kind of an assumption on our point, and we're kind of skipping over some ideas of what we can do with that right there. We're actually using that idea to say that these two iterated integrals should result in the same value, because we want them to both represent the volume of the solid. If we don't know if that's true, then that they do represent the volume of the solid, then we can't really say that they will give us the same value. But that's what Fubini's theorem is telling us, and he did all the work. We'll just kind of take his work for granted here and just roll with it. But basically, as long as we have a sufficiently continuous function, it doesn't have to be continuous everywhere, but continuous for most of the rectangle, that our iterated integrals will represent our volume. They will be the value of our double integral, and we'll just that's all we want to know. But what you might really be wondering is why we're making such a big deal about this. Why does it matter that we have two different ways to compute the double integral? Why not just stick with one of them? Like this is essentially our the formula that we derived originally. Why don't we just stick with that and say that's all we need to do? Well, it might turn out that one of these will be easier to compute than the other one. So let's actually look at an example of that. So in this problem, they want us to compute a double integral. They don't actually tell us it is a double integral, it's not an iterated integral, so they're not really telling us what order to do the integration in. But we do have a rectangle that we're integrating over, and we have this function. So there are going to be two ways to do this by Fubini's theorem. So we could, let's do, we have the integral from 0 to 2, 0 to 3, so these are two intervals here. Our function y e to the minus xy. So the 0, 3 here needs to correspond to the first variable we put over here. That's our y variable. And then we have our x variable corresponding to the 0, 2. So that's one way of doing it. The other way would be to do these in the opposite order. So from 0 to 3 and then 0 to 2, the same function in there, but this time it's dx dy. These are both two ways of actually computing this double integral. But if we were to use this first way, so kind of think of this as y e to some constant times y, how would you compute, how would you integrate that function with respect to y? Now, the main way that you would do it using the techniques that you would have covered in Calc 1 and 2 would be trying to use integration by parts. Something we definitely could do if we wanted to, but we kind of like to avoid. We would rather only have to worry about substitutions if we can. So let's see if we can get away with the second one and not have to do integration by parts. So I'm going to do this integral here. So let's go ahead and even just move it down here. Just kind of copy it over there. We'll do exactly what we did on the previous problem, where we integrate from the inside out. So we're going to integrate this function with respect to x. And the result of that, we are going to evaluate from 0 to 2, and then we'll integrate that one, so that should be dy. Pay attention to what variable you're doing. Alright, so we are integrating y e to the minus xy with respect to x. Keep in mind, that is going to treat y as a constant. So we really just have a constant times e to a constant times x. And we want to integrate that. Now, how do we integrate that? Well, if you want a reminder on how to handle that, you might do something like u equals minus xy. So substitution, so we'll be integrating e to the u. In fact, maybe I'll even write all this out. So we'll go ahead and remove that for now. We're going to change this to an integral with du, where u is equal to minus xy. Du then, remember, we're differentiating with respect to x here, because we're not even considering y as anything but a constant until we're done with this integral. So derivative of minus xy with respect to x would be minus y, and then we have our dx. Or in other words, dx, the dx that we have here, which actually we already have a y there, so we'll keep the y dx, but we'll move the negative to the other side. So the y dx that we have here is going to be replaced with a negative du, so we'll have a negative, and then this is e to the u. We'll have to figure out what this is. Well, I'm just going to leave it as from x equals 0 to x equals 2. We'll come back to x's. I don't want to put variables up into my... I don't want to deal with the y here in my limits for the moment. We'll get into that in the next section. We still have the integral with respect to y on the outside. We integrate minus e to the u with respect to u. So e to the u just turns into another e to the u. So we have a minus e to the u, but u is negative xy. And that's going to go from 0 to 2. Or in other words, what we've done here is using a substitution, the y that was outside that was giving us trouble and making us want to use integration by parts ends up just kind of being absorbed into the exponential itself. We don't really have to do anything with it like we would have had to do here. Now we do need to go ahead and put in our limits. So first we go ahead and put in 2, so we have a minus e to the, now remember this is for x, so minus 2y. Then we subtract, or really add because of the minus sign there, e to the 0, because that's, the 0 is just going to get rid of everything. E to the 0 is 1. Now we just do everything like we did before. Technically, we do have to use a substitution like we did here. In this time, we might say u equals minus 2y. I'm going to kind of skip over that. I'll let you, because this one doesn't have to deal with any of the extra variables, so a little easier to see. But what we're going to have for the integral of negative e to the negative 2y is 1 half e to the minus 2y. Integral of 1 is y, and we're integrating from 0 to 3. Go ahead and put those in. So we have a 1 half e to the minus 2 times 3, or e to the minus 6. Then we get a plug in 3, so we get a plus 3. Then we subtract what we do when we get when we plug in 0. Well, we don't get all zeros. We have 1 half e to the 0, which is minus 1 half, and then plus 0. So we subtract 1 half, and I guess we could write this as 1 half e to the minus 6 plus 5 halves. Or however you want to write that. But the important thing here is that we got away with only doing substitutions and no integration by parts. In fact, in more complicated problems, it could actually be one way would not be possible to do. You might run into some integral that you do not know how to integrate, whereas the other one might just work itself out. So it's a little hard sometimes to tell whether or not one is going to work or not. You just kind of have to try whichever one you want. Just pick one and see what happens. And if it doesn't work, you can try the other one. That's really the only rule of thumb for this. And again, I keep referencing that we're going to get into a little bit more complicated versions of this when we don't just work with rectangles, and it will turn out to have the exact same kind of issues where one might be a lot easier than the other one. But for now, we're just working with rectangles. Let's work on another problem. So initially, this might look more complicated because it has a secant in it. But don't be too worried about it. Again, there's 2 ways to set this up. I'm just going to pick one, and if we run into a problem, we'll go ahead and do the other one. But this one will actually work out very nicely, so we don't really have to worry too much about it. I'm going to go ahead and do them in the order that they have them here. So 0 to 2 for x's, so the dx will be at the end. Then we'll go from 0 to pi over 4 for y's. We have x secant squared y dy dx. Now there is something kind of interesting that happens here. Notice that when we do this integral, we're integrating with respect to y. In that case, x is a constant. And when we're doing integration, or even differentiation, constants can just be pulled out. We're not going to be doing anything there. You're just basically going to take the integral of secant squared of y, and then multiply the result of that by x. Why don't I just pull that x out? We have x times the integral from 0 to pi over 4 of secant squared y dy. Just x times that integral. Whatever the result of that integral is multiplied to x, and then we integrate that with respect to x. In fact, this integral that we have inside here doesn't have any x's in it. So as far as the integral with respect to x is concerned, this thing's just a constant. We could pull it out. So here we took our x and pulled it out. Here we're going to take this entire integral and pull it out. I'm put it at the back, but it's really just like we multiplied the integral of x from 0 to 2 by this integral with respect to y. In essence, what we've done here is we were able to split up our integral into a product of two integrals. This is actually something that we can do in general. We actually have a formula for this. As long as our integrand, the function that we have inside our double integral, is just the product of a function of x with a product of a product of a function of x with a function of y, then we can get this formula. So here our integrand is just g of x times h of y. Neither one of these functions depends on the other variable, and we can split up our double integral into just the product of the two integrals. So the integral of g of x with respect to x over this interval, and then the product and then the integral of h of y with respect to y over the interval c to d. That's something that you might want to look for if you can. It's definitely not going to happen all the time, but if it does happen, if we can split up our integrand into a product of two functions that do not share a variable, then just roll with it. You don't have to do all of it all at once if you don't want to have to. That does mean that we can go ahead and compute these two Calc 1 integrals separately. I'm going to go ahead and do those both on the same line, but you could do them on separate lines if you want to. We have the integral of x, which is 1/2 x squared. That's going to be evaluated from 0 to 2. Then we're going to multiply by this integral here. Now, you might think, well, we're dealing with secant squared, but just remember, tangent of y differentiates into secant squared, so the integral of secant squared is tangent of y. And that's going from 0 to pi over 4. Then we have, this is 1/2 of 2 squared is 2. Then we subtract 0 from that. Over here we have tangent of pi over 4. Tangent of pi over 4 is actually 1. Then we have minus tangent of 0, but that's just 0. So we end up with 2 times 1, or just 2. That is our double integral. Now, of course, we could have done this just directly. We could have gone ahead and integrated this, and originally we'd have, what, x times 1, and then we'd end up integrating with over x, and we get the same result. But just things that we can look for. Now, one last topic that we're going to cover in this section is the concept of average value. You may remember the formula for the average value of a function of one variable over an interval. So if we have a function f of x over the interval from a to b, the average value of that function over that interval is just the integral of that function over the interval divided by b minus a. And the b minus a here is that it's the length of the interval that we're integrating over. Basically, we're summing up all the values over that interval, and then we divide by the length that we're going over. In a sense, what we're kind of doing there is what we're doing with when we normally calculate averages. So if we have, say, a1 through an, you add up all the values, and then you divide by how many there are. When you're doing that for a function, you're adding up is taking the integral, and then dividing by the number of that you have is dividing by the length of that interval. For a function of two variables, we instead of dividing by the length, we just divide by the area of the region that we're integrating over. And of course, we'll do a double integral instead as our way of adding up the values. So here we have a function f of x and y that we want to find the average value of over a rectangle R. So we take the double integral over that rectangle, and then we divide by the area of the rectangle. and that's going to be our average value. And honestly, that's really all that we had to say about average values, as long as we're looking for the average over a rectangle. If we do have a more complicated region we're trying to find the average over, we would end up replacing the rectangle with whatever that region is, and that would make the double integral a little bit more complicated to find, and finding the area of such a region would be a little more complicated as well. We might have to do an integral there as well. But again, we are going to leave that for a later section. Assuming the book actually comes back to this idea, but the formula will still remain the same, even if the book never comes back to it. But let's go ahead and work out an example. So we have a function here, x squared times y. We have a rectangle. It just gives the vertices this time. It might help to kind of think about what those vertices are. So this point down here, this would be our -1 for our x and 0 for our y. Then we have the point -1, 5, so that would be this point over here. Well, I guess that'd be this point over here, sorry. We have -1 and 5 for our y. Then we have 1 for our x and 5. So the third point listed here is 1, 5, this point over here. And then finally 1, 0, that would be this point here, 1, 0. So it's this rectangle here. Of course, when we try to find the average value, we're going to take the double integral and we're going to divide it by the area of the rectangle. In fact, the area of the rectangle is pretty easy to see here. This side down here, this has a length of 2. Mine is going from -1 to 1, so that's a length of 2. And this side over here has a length of 5. So the area of the rectangle is going to be the product, 10. Easy enough. The double integral is going to be a little bit more fun. Double integral of this function over r. We're going to turn this into an iterated integral. Again, it really doesn't really matter which order we do it in. In fact, we can make use of the formula that we just found in the last problem because this is just the product of x squared with y. So we could actually just take the integral of the x squared over x times the integral of the y with respect to y. We can kind of even skip out writing it as an iterated integral if we want to. Of course, x's are going from -1 to 1. Y is going from 0 to 5. If we go ahead and integrate this, integral of x squared is 1/3 x cubed. Integral of y is just 1/2 y squared from 0 to 5. Go ahead and plug in our values here. So putting 1, we get a 1/3. Then we subtract what we get when we plug in -1, but when we plug in -1, this becomes a -1/3, so we end up adding a 1/3. Here we plug in 5, we get 25 halves minus 0, so we'll just leave it as 25 halves. So we'll end up with a 2/3 times 25 halves. The 2's will actually cancel each other out. We end up getting a 25/3. Of course, that's not our answer. Our answer, we take this double integral and we divide by the area. So our average value, f average, is going to be our integral of 25/3 divided by our area of 10. Or we can go ahead and simplify this. Divide out 5 from the 25 and the 10. So we get a 5 on top. We're left with an extra 2 down here. 2 times the 3 that we have there is going to be a 6. So 5, 6 is our average value. Let's go ahead and actually plot this and see how they compare. So I'm going to go ahead and put in my function, f of xy is x squared y. That's this surface here. Of course, we don't really care about the entire surface. We're only going to care about the part that's in our rectangle. So our rectangle is -1, 0. We had -1, 5. 1, 5, and 1, 0. Those were the 3 points that they gave us. Let's go ahead and shrink those a little bit so they don't stand out too much. Sometimes it gives me bigger points when I don't want them, and sometimes it gives me smaller points when I do want them. Want bigger ones. Oh well. And I'm going to go ahead and make a... Ah, shoot. Messed that up. Here. I want to make that rectangle. There we go. So we can kind of see the rectangle in there. Stop it. And then I'll go ahead and use the surface command to actually only look at the part that's in there. And again, don't worry too much about the actual construction here. Though at least for these surfaces where you're going over a rectangle, it's not too hard to figure out exactly what I'm doing. But so I gave that surface. It's really, you can kind of see it in there. It's showing only the portion of the bigger surface over that rectangle, and I'll go ahead and leave that out so you can see a little bit better. So don't want to go too far. So we're looking at the average value of all the heights. So we've got a whole bunch of heights here, and we're looking at what is the average height of this section of our surface. Now, from what we just did, we calculated that average height to be 5/6. So let's look at what the height of 5/6 would actually be. It would be this plane here. And it's saying on average, the height of the surface is equal to the height of this plane. So there's a lot of points in the middle that are below the plane, and they're kind of evening out all the points that are way above the plane. That's the way you might think about it. Another way you might think about it is if you calculate the volume under this surface above our rectangle down here, that volume would actually be exactly the same as the volume underneath this plane above that rectangle. Though, of course, that logic only really works if we are dealing with something that does have volume. If our surface dips below the x-axis or the xy plane, that won't necessarily make as much sense. But if we could still talk about, say, negative volumes versus positive volumes and all that kind of stuff, and still make it have some sense. But the point here is that this is a nice way to talk about the average value, and a nice way to actually compute what that would be. Alright, but I've rambled on a little bit too much here. I'm going to leave this section here. Most of this section has only been about the theoretical framework of what double integrals are. In fact, the entire first video was all about the theory and not really about the computation. In the next section, we will remove this restriction of integrating over a rectangle, so we can actually look at more general closed regions of the plane. And that's where things will get a little bit more fun, so look forward to that. But that's all I really like to say for now. So I'll see you in the next section.